Depth of field is an important artistic element in film and photography fields. It represents the distance between the nearest and furthest objects of a scene that appear to be sharp. The blur that is produced from seen objects outside the depth of field often shows a lens-specific character, which is referred to as bokeh. The appearance of the bokeh depends on an often complex lens system, which often includes optical distortions and a characteristic shape of the aperture. Three-dimensional compositing with a photo or video footage that makes use of depth of field and bokeh requires simulating the bokeh on virtual objects which are placed outside the depth of field. Since the appearance of the bokeh might include specific lens characteristics, precisely simulating the bokeh has been challenging. We introduce NeuralBokeh, the first approach for learning to believably simulate the bokeh that appears in a specific photograph of a film sequence. Our network learns a specific bokeh by processing many pairs of an all-in-focus image and a circle of confusion map into a defocused output image. The output is compared to a ground truth defocused photograph that corresponds to the circle of confusion map. To learn spatially varying bokeh, we split the input rendering into overlapping tiles, which we process separately, but evaluate in conjunction during training to avoid color differences between tiles. The bokeh is learned precisely by concatenating residual blocks with per-channel convolutions of increasing size, up to a maximal size that is correlated to the supported range of depth and focal distance. At runtime, the input to our network is an RGB photograph, its metadata, including the size of the aperture and focal length, an optional object mask to handle occlusions, and an all-in-focus RGBD rendering of virtual scene objects to be inserted via 3D compositing in the photograph. Depending on the circle of confusion map, the network is applying spatial varying learned bokeh to the input rendering. The processed tiles are assembled into the blurred rendering, which is subsequently composed into the final result, using the input mask and a blurred mask of the rendering. Our approach introduces several novel network design choices, which we validate on several synthetic datasets that include images with distinct bokeh shapes. We use ResNet blocks with an increasing kernel size of up to the size of the largest possible circle of confusion, and hyperbolic tangent activation after each block. To demonstrate the impact of this design decision, we compare our results to its variant that uses ResNet blocks with a fixed kernel size. We use 3x3 kernels. Note that we use the same number of network layers as NeuralBokeh, because we noticed that adding one more layer of ResNet blocks exceeds the memory consumption of NeuralBokeh. To learn spatially varying bokeh, we split the input image into tiles. To validate the input tiling, we compute results with and without tiling. To learn to avoid color differences in neighboring tiles, we extend tiles so that they overlap at their border and compute the loss over the entire image. To assess the output quality of NeuralBokeh, we compare our results to those achieved with state-of-the-art approaches for deep learning lens blur. NeuralBokeh has been developed for compositing photographs with 3D renderings. Since it produces temporally coherent bokeh, it can also be used for film productions.